Thank you. So let's just begin with a brief recap of last time. So last time I told you Atiyah's definition of a topological quantum field theory, that it would be a tensor functor from a category of n-1 manifolds and Cobordisms between them into the category of, say, complex vector spaces. And I argued that this structure is maybe not really as much as you'd like to see. What you, in many cases, and this is something that I'll talk about more in this lecture and in future lectures, you see more structure. This sort of structure is accompanied by other structures which assign invariance not only to manifolds of dimension n and n-1, but also to manifolds of lower dimension. And if you want to think about that kind of structure, it's natural to try and describe it in the language of higher category theory rather than ordinary category theory. Because if you want to think about manifolds, say, of dimension n, n-1, and n-2, well, you can imagine that your manifolds of dimension n-1 are Cobordisms between your manifolds of dimension n-2, and your manifolds of dimension n are Cobordisms between those manifolds of dimension n-1. So you have some sort of structure where you have not only morphisms, but morphisms between the morphisms. And that's what higher category theory is all about. So let me begin by reviewing just the definition of a category, the ordinary category. So definition, a category consists of, first of all, a collection of objects, or let's call our category something C. Objects, which I'll denote by capital letters X, Y, Z, and so forth. 2, for every pair of objects, a set Homs in C from X to Y, and 3, an associative composition. Well, let me first say a composition law Homs from X to Y cross Homs from Y to Z maps to Homs from X to Z. And fourth, a condition that this composition law should be associative. And that there should be units with respect to this composition law. So this is the usual definition of a category. Sorry?
Units.
And with units. Thanks. So you can. So let's try and generalize this in a naive way to discuss a mathematical structure where you have not only objects and morphisms between them, but also morphisms between the morphisms. So let me give the definition of what I'll call a strict 2 category. It consists of, well, it's going to be very similar, a collection of objects, X, Y, Z, and so forth. For every pair of objects, you'll have morphisms between those objects, but rather than just forming a set, those are going to form a category. And now, as before, you want to require that you can compose morphisms. So before, that was a map of sets from this product into this set of Homs from X to Z. But now, since Homs form categories, I'll say that this is given by, well, composition functors from Hom XY, Hom YZ, into Hom XZ. And now, we should again demand that this be associative. And I'm calling this a strict category because when I say the fact that I'm defining a strict category is reflected in what I mean by associative here. This is associative on the nose. That is, if you have 4 objects, W, X, Y, Z, and you consider the various ways that you can get from Hom Wx, Hom xy cross Hom yz into Hom wz. There's two natural composition functors you could write down. Here we're requiring that those actually be identical as functors. So let me try and give an example of a strict 2 category. So first, let me try and give an example of a 1 category. So let X be a topological space. So probably everyone here is familiar with the fact that if we choose a base point in X, you can define a group, the fundamental group of X with that base point, pi 1 of X, comma X. This is a group whose elements are paths in the space X that begin and end at the base point. Or more precisely, homotopy classes of such paths. And the composition law on your group is given by concatenation of paths. So this is an important invariant of a topological space. But now suppose that I gave you a topological space and I didn't give you a base point. Well, you can't define the fundamental group, but you can define maybe a little bit more of abstract an invariant. If you don't choose a base point, choose X, then you can define something that's an invariant of the space big X alone. I'll write it as pi less than or equal to 1 of X. This is called the fundamental groupoid of X. And this is going to be a category whose objects are points of X. And whose morphisms are given by homotopy classes of paths. And again, composition in the fundamental groupoid is given by concatenation of paths. So this fundamental groupoid of X knows a little bit more than the fundamental group of X. It knows, for example, about pi naught of X, the set of path components of X. That's the set of isomorphism classes of objects in this groupoid. It also knows about the fundamental group of each connected component. The fundamental group of each connected component is the automorphism group of the corresponding object of the fundamental groupoid. So this fundamental groupoid knows something about the topology of X, but it doesn't know very much. It knows about pi 0 and pi 1, but it knows nothing about the higher homotopy groups. So if you wanted to capture something about the higher homotopy groups of X, you might try and do it using the language of higher category theory. So let me try and define a more elaborate structure. So definition sketch. The fundamental 2 groupoid of a topological space X, or let me call this pi less than or equal to 2 of X, is a 2 category defined roughly as follows. So the objects are going to be points of X. The morphisms are going to be given by paths in X. And the 2 morphisms, or morphisms between the morphisms, are going to be given by homotopies between paths. And now we'll consider 2 such homotopies to be the same if they're homotopic to one another. So here I just described a structure and I called it a 2 category. Now, can you fit it? Can I describe it more precisely using the language that I introduced over here? Can you actually define a strict 2 category that implements the idea that I have described on the right board? Well, we have a collection of objects. We'll just take our collection of objects to be the points of X. And for every pair of objects, X and Y, I want to extract a category, well, I can define that category to be the ordinary fundamental groupoid of a certain space, namely the space of paths from x to y. But now we run into a little bit of trouble when we try and describe these composition functors. Because what do I mean by composition? What is a path from x to y? A path P from x to y is, say, a map from the unit interval in my space such that P of 0 is equal to the point x and P of 1 is equal to the point y. And now suppose I had another point, so let's draw a picture. Here's my space x, here's little x, here's little y, and here's little z. So here's my path P, and now suppose I had another point Q from y to z. So that's a map from 0, 1 into x such that Q of 0 is equal to y and Q of 1 is equal to z. So what do you mean by concatenating these paths or composing them? Well, one thing that you might mean is the path that's gotten by traversing both of these paths but doing each one twice as fast. So you could define this to be a map from 0, 1 into x such that, let's say, Q circ P of t is P of 2t if t is between 0 and a half, and Q of 2t minus 1 if t is between a half and 1. So if that's what you mean by composition, then you run into a little bit of trouble here, because composition is not associative on the nose. If you have three paths, P, Q, and R, and you compose them, well, the order in which you compose them is going to matter a little bit. If first you compose P and Q, and then you compose the result with R, well, what you're going to end up with is a path where first you traverse the path P at quadruple speed, then you traverse the path Q at quadruple speed, and then you traverse R at double speed. If you were to compose these in a different order, well, you would end up partitioning the unit interval a little bit differently. And you'd end up with a path where first you traversed P at double speed, then you traversed Q at quadruple speed, and then you traversed R at quadruple speed. So why isn't this a problem when you're defining the fundamental groupoid? Well, it's because morphisms in the fundamental groupoid are not literal paths, they're homotopy classes of paths. And these two paths, while they're literally different, there's a natural homotopy from one to the other, which is just given by sort of stretching out the unit interval. On the other hand, when we talk about the fundamental 2 groupoid, one morphisms there, that is objects of these Hom categories, are literal paths. And so we run into some trouble if we want composition to be associative. So there are two ways that we might try and address this trouble. The first is try and massage the definition of the fundamental 2 groupoid. After all, I just said that one morphism should be given by paths, but why should a path mean a path parameterized by 0, 1? Why can't it mean, say, a path that can have variable length? And then my composition of paths could be a composition where when I compose paths, the lengths add. If I do that, well, I can arrange that composition is strictly associative, and this problem would go away. But another thing I might do is fiddle with my definition of a 2 category. Say that this is really a problem with the definition that I've given here. I shouldn't really be requiring associativity on the nose. In this case, where composition of paths is not strictly associative, it's associative up to homotopy. And that translates into here that this associativity is true not on the nose, but up to isomorphism. That is, the 2 natural functors that I get from Hom wx cross Hom xy cross Hom yz into Hom wz, those two functors are not literally the same, but there's an isomorphism between them. So in this case, it doesn't really matter which of these approaches that you take. So let me mention there's so there is a more elaborate definition. Of non-strict two-category, or what people sometimes call a bicategory. Where associativity is not required to hold on the nose. It's required to hold up to isomorphism instead, but more than that, it's required to hold up to specified isomorphisms that are part of the structure of a two-category. And moreover, these isomorphisms themselves have to satisfy some sort of coherence conditions that reflect that some sort of higher associativity law is being satisfied. So I'll summarize that by saying this is true up to coherent isomorphism, and I'm not going to specify exactly what this means, although at the end of the lecture I'll describe one way of encoding this idea of homotopy theoretically. So in the case that I was describing, it's not really necessary to, well, in the case of two categories, it's not really necessary to worry too much about the difference between strict categories and non-strict two categories, because there's a rectification procedure that will replace any non-strict two category by a strict two category which is equivalent to it. And more or less, this is an abstraction of the idea that I described for the fundamental two-groupoid, which is instead of just taking paths that are parametrized, allow your paths to have variable lengths. So that idea has some sort of generalization which applies to any non-strict two-category. But if we want to study extended topological quantum field theories in large dimensions, we need to think not just about two categories, but about higher categories where we have morphisms of many different levels. So now let's try and generalize. Replace this 2 by an n. So a strict n category is supposed to consist of, well, a collection of objects, x, y, z, and so forth. And now for every pair of objects, instead of having a category of Homs from x to y, we'll have an n-1 category of Homs from x to y. And we should again be equipped with some sort of a composition functor, and that composition law should satisfy associativity and have units. And here, this is a reasonably precise definition of a strict n category if you require associativity on the nose. But there's supposed to be an accompanying notion of a non-strict n category where the associativity only holds up to coherent isomorphism again. So what's an example? If X is a topological space, well, you're supposed to be able to generalize the fundamental groupoid and the fundamental two-groupoid to produce an n category, which I'll denote by pi less than or equal to n of x. This is something that is sometimes called the fundamental n groupoid of x. And how can it be described informally? Again, the objects are points of x. One morphisms are given by paths. Two morphisms are given by homotopies between paths. Three morphisms are given by homotopies between homotopies, and so forth, until finally the n morphisms are given by, I don't know what you want to call these, n-fold homotopies. And at the nth level, you identify two n-morphisms if they themselves differ by a homotopy. So this is supposed to be an example of an n category, and it's actually, if n is at least 3, these sorts of n categories cannot be fit into the strict framework that I described over here. That is, this sort of problem that I described, composition, you want to say it's given by concatenating paths, and if your paths have length 1, then you run into some trouble with associativity. So for n equals 2, there's some ad hoc ways you can get around that. If n is at least 3, there is no ad hoc way to get around that, and these fundamental n groupoids are, if you define them properly, they're examples of non-strict n categories that don't.
The length change?
So the length change is sort of geared to paths, but if you then want to think about higher dimensional things, you could sort of imagine that length is not all you would need to keep track of, and it might be really complicated to, you want to be sort of composing things in multiple directions, and exactly. So it turns out that that's a real issue. There's no way to get around the fact that that definition over there cannot be put into this framework.
Is there, I can think of two possible obstructions, the action of the fundamental group on the higher homotopy groups or Whitehead brackets, but those might have occurred at n equals 2. And is there an obstruction that one can articulate?
Yeah, but I'm not sure. Well, so what's that? Well, so I'll give a quick answer. So suppose that you have an object in a category C. And let's say we're dealing with a groupoid, so everything is invertible. So X is an object of C, and you look at Homs in C from X to X. So this is going to have the structure of a group. And now if you're in a 2 category, that's not just going to be this is not going to be a set anymore, it's going to be a category. But the replacement for that being a group, or having this composition law, is telling you that that's a monoidal category, that there's some kind of tensor product on that category. And now if this was a strict 2 category, then you would actually know that that was a strict monoidal category, where the associativity isomorphisms were the identity maps. So now if you were in a 3 category, suppose you were to look at something like this. This gets sort of 2 compositions on it. One composition coming from the fact that this is monoidal, and one composition from the fact that this is, you're homming something to itself. So if you were in just an arbitrary 3 category properly formulated, you would know that you had 2 monoidal structures on this category, and so it was a braided monoidal category. But if everything was strict, then you would know that those monoidal structures were strict and the compatibility was strict, and you would know that it was a symmetric monoidal category. And now in the fundamental groupoid example, let's say you look at pi less than or equal to 3 of the 2 sphere, right? Then what is the category that you're trying to extract? So you take, say, loops 2 of the 2 sphere. That's well, that's a category whose objects are elements of Z, homotopy classes of maps from the 2 sphere to itself, but there are also automorphisms that come from pi 3 of Z. And that has a braided monoidal structure which is not symmetric. You can actually see sort of hop invariant coming up when you consider what the braiding does. So n is equal to 3, x is equal to S2 is a counterexample. All right, so I want to call your attention to one feature that these examples have. This is called I'm calling this an n groupoid rather than an arbitrary n category. That's because all of morphisms at all levels here are invertible. So let me give an informal definition here. An n groupoid is an n category where all k morphisms are invertible. For k at all levels. So, for example, the inverse, a one morphism in this category is given by a path, and the inverse of that path, just as in the ordinary fundamental group, is given by the same path but read in the other direction. So it turns out that the theory of n groupoids is quite a bit simpler than the theory of n categories in general. So you could imagine taking some sort of a limit here as n goes to infinity of this example. So let X be a topological space. You can define something that I'll call the fundamental infinity groupoid of X by just writing a dot, 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 and not ever stopping at any level. This is some sort of a structure where you have objects which are given by points of X, one morphism is given by paths, two morphisms are given by homotopies, so on and so forth, and at no level do you ever mod out by homotopies or do you ever stop. So this is an example of something that you might call an infinity groupoid. It's some sort of a higher category in which all morphisms are invertible at all levels. And in fact, it's the characteristic example of something like that, or it's in some sense the only example. So let me make an assertion. So the construction that I just vaguely outlined, which takes a topological space X to its fundamental infinity groupoid, determines, say, a bijectin between topological spaces up to weak homotopy equivalence with infinity groupoids up to equivalence. So why am I calling this a thesis? It's because I haven't really given you any definitions. I haven't defined what I mean by an infinity groupoid, or said when they're equivalent, or given a precise implementation of this construction that constructs the fundamental infinity groupoid of a space. But this thesis is something which should be true anytime you give a definition. It's a litmus test for whether or not a definition of higher category is a reasonable one. Any reasonable definition of higher category should be such that if you restrict your attention to higher categories in which all the morphisms are invertible, then what you recover is just classical homotopy theory. So you can either regard this as a test that any definition has to pass. Oh, and by the way, I should mention that, as I've already explained, this definition over here, strict n categories, would fail that litmus test because, for example, well, you can't implement this construction on the two-sphere.
Why is that a reasonable litmus test? I believe you, but why?
Well,
why should you refuse to accept that infinity categories could be a larger concept than topological spaces?
well, I don't know.
He didn't define precisely what it was a litmus test of.
Well, my question is
For reasonable working definition, I mean, one thing you could say is that for reasonable working definitions where you can set up a good theory, this is true. And so you could either take this as a litmus test, or you could take this as the first step in giving the definition of a higher category. So you could, for example, rig your definition so that this was going to be true manifestly. So, for example, you could give the following definition: an infinity groupoid is a topological space. And when I say topological space, I really mean just something that you can do homotopy theory with. So if you're familiar with the theory of simplicial sets, maybe an even better thing to say is a Kahn complex. So, so far so good. So that gives us a definition of the notion of an infinity groupoid. But of course, we probably want to talk about higher categories in which not all the morphisms are invertible. So I didn't give you the definition of an n category because if you try and sort of spell out what you mean by associative up to coherent isomorphism, it gets very complicated very quickly. But over here, we sort of got around that, at least in the situation where we required all of our morphisms to be invertible. You get around that, this description of what it means to have an infinity groupoid, just meaning you have a topological space, you never have to contemplate what you mean by these sort of higher consistency conditions. They're sort of shoved into the background, imagining that there's some construction of the fundamental infinity groupoid which you're not even going to specify because you're just going to define it away. So the upshot of this discussion is that it's much easier to discuss higher categories in which you assume lots of morphisms to be invertible. So now let me introduce an informal definition. I want to sort of take advantage of that. Let me define, say, an infinity n category. Is a higher category where all k morphisms are invertible. For k greater than n. So for example, an infinity zero category is just a higher category in which all morphisms at all levels are invertible. These are the same thing. That's what I called an infinity groupoid. And according to the thesis, which I just erased, that should be the same thing as a topological space. So let's try and implement this idea on the left board, where we take as our starting point not sets as zero categories, but instead infinity groupoids. So let me adjust this definition a little bit. We ought to be able to give some sort of an inductive definition of an infinity n category. It's something which has a collection of objects, x, y, and z, and so forth. For every pair of objects, I have an infinity n-1 category of morphisms between them. And I have some sort of composition law. And I should require associativity. And now let me write maybe up to isomorphism. This is not a precise definition yet. But this is the sort of flavor that you might expect an inductive definition of infinity n category to have. So we could try and implement this when n is equal to 1. What is an infinity 1 category? Well, so let me write it here. Example. An infinity 1 category, according to this sketch of definition, that's the same thing as what you might call a topological category. That is, a category enriched over topological spaces, or in other words, a category in which on all of these Hom sets you have topologies and these composition laws are continuous. So that's what you would get if you took this definition literally and you required associativity on the nose. Now you might object at this point and say, well, maybe you shouldn't be requiring associativity on the nose. Maybe you really want to require it up to isomorphism, which in this using topological spaces as our representatives for infinity groupoids would mean that in some sense this composition was only supposed to be associative up to homotopy. Well, just like with strict two categories and non-strict two categories, it turns out not to matter here. You can require that your topological categories have an associative composition on the nose, or you can require that they only have an associative composition up to coherent homotopy. So let me write that as topological categories which are associative up to homotopy. And it turns out that there's lots of other things that you can write here that turn out to be implementations of the same idea. So topological categories which are associative up to homotopy. There's the theory of quasi-categories. There's the theory of Siegel categories. And there's a theory which I'm going to describe later on in this lecture called the theory of complete Siegel spaces. And they're all different ways of sort of giving a precise implementation of the idea that's sketched on this left-hand board. So at this point you might be asking me why I have bothered introducing this abstraction of an infinity n category. After all, weren't n categories themselves bad enough? So there are two answers that I can give to this. One is, if you want to define the notion of an n category for large n, it's actually probably easier to first define the notion of an infinity n category and then specialize to the case where you don't have morphisms above degree n. So you can see this already in the case of groupoids. So according to the thesis which I erased, an infinity groupoid is really more or less the same thing as a topological space. So then what's an n groupoid? Well, that's something that you should think of as being given by a topological space where you have no homotopy groups above degree n. And if you just look at the number of words that it takes to say topological space or topological space with no homotopy groups above degree n, you see that it's maybe the first one that's the simpler concept. And that's true not just for groupoids, but also for these infinity n categories in general. And the second reason is that thinking about these infinity n categories is actually going to give us, lead to some interesting, it's going to be useful to us in contemplating topological quantum field theories. So that's what I would like to explain now. So let's take let's table this discussion of higher categories for a moment and return to the discussion of topological quantum field theories. So let me give a couple of examples. So I'm going to give you some examples of two-dimensional topological quantum field theories, and they won't quite be examples. They won't quite fit into the definition that I gave yesterday. So I'll say almost examples. So example number one, what I'll call the B model. So let A be an associative algebra over the complex numbers. If you have an associative algebra, you can regard it as a bimodule over itself. Or in other words, you can regard it as a module over A tensor the opposite algebra. So let's recall a definition. The Hochschild cohomology groups of the algebra A are defined to be the X groups of A with itself, where we regard A as a module over A tensor A op. And here all tensor products mean tensor products over the complex numbers. So here you have a definition of the Hochschild cohomology of an algebra. Now, if X is an affine variety, over the complex numbers, you could write X as spec A, where A is some algebra. And you can define the Hochschild cohomology of X to be the Hochschild cohomology of this algebra. So this defines for you the Hochschild cohomology of an affine scheme. But you could generalize this definition. You can sort of globalize it to the non-affine case as well. There's a definition of the Hochschild cohomology of, say, any C scheme, which is roughly speaking given by taking some affine cover, taking the Hochschild cohomologies of those affine pieces and gluing them together in some way. So these Hochschild cohomology groups always form an algebra, where the algebra structure is given by composing in X using the Yoneda product. It's actually a commutative algebra, and if X is, say, an n-dimensional variety, let's say a smooth n-dimensional variety, then you can compute what its Hochschild cohomology looks like in degree 2n. And what you find is that the Hochschild cohomology in degree 2n is just the nth cohomology of X with coefficients in the top wedge power of its tangent bundle. Now, this is maybe a little bit suggestive. So remember that a two-dimensional topological quantum field theory is given by a commutative algebra with some sort of a non-degenerate trace on it. And this almost looks like something that could support a trace. If instead of the top wedge power of the tangent bundle, I had the top wedge power of the cotangent bundle, there's a canonical trace map here. So in order to get that canonical trace map, I need to restrict my attention to some kind of X where I can't tell the difference between the top wedge power of the tangent bundle and the top wedge power of the cotangent bundle. So now let's assume that X is a smooth n-dimensional Calabi-Yau variety. What that means is that the top wedge power of its tangent bundle is trivial, and therefore so is the top wedge power of its cotangent bundle. So in that case, you do have this canonical trace map, and Serre duality tells you that in fact the trace pairing is non-degenerate. So Serre duality implies that this Hochschild cohomology algebra is a Frobenius algebra. Well, so here's where I get to the almost part. I want to say it's a commutative Frobenius algebra, but the product on Hochschild cohomology is commutative in the graded sense. So this is an example of a commutative Frobenius algebra, not in the category of ordinary vector spaces, but in the category of Z2 graded vector spaces. But that's just not really an issue. So by the Folk theorem, which I talked about earlier this week, this tells you that you have a two-dimensional topological quantum field theory whose value on the circle is this Hochschild cohomology. So here's an example for you. Let me give another example. This example is based on work of Dan Fried, who's right behind me, and his collaborators. Mike Hopkins and Konstantin Telemann. So let G be a compact Lie group. And suppose that you're given a level, meaning a class in H4 of the classifying space. Then you can use L to define a central extension of the loop group, where this loop group means maps from the circle into G. And then you can contemplate representations of this centrally extended loop group. And now if your level was chosen sufficiently positive, that there's a nice theory of these representations. And in fact, there's some unexpected structure on these representations. There's some sort of a tensor product on them given by fusion. And now in particular, you can look at, well, here by rep, let me mean not the category of representations, but say the Grothendieck group of representations, or the representation ring. This has a ring structure which is determined by this fusion product. This thing is called the Verlinde algebra. Now, the work of Fried, Hopkins, and Telemann gives an identification of this Verlinde algebra with something else. This is isomorphic by their work to some sort of twisted K-theory, twisted equivariant K-theory of G acting on itself by conjugation. So here tau is some twisting which depends on the level. So this, another model for the G equivariant K-theory of G is that you're actually trying to think about the K-theory of the orbifold, which is classifying flat G bundles over the circle. And in fact, this Verlinde product, in good cases, it's equipping this with the structure of something like a Frobenius algebra. Now it's not, this is again an almost example, because this thing is not a Frobenius algebra over a field, but it's now a Frobenius algebra over Z in good cases, or maybe a Frobenius algebra over K-theory in all cases. This thing here gives you, this is the value of a circle on a circle of a topological quantum field theory, where that topological quantum field theory, if you want to see what it does on a surface, say, then you think about flat G bundles on that surface and play some games with their K-theory of that moduli space. So I'm not going to go into the details, but let me just put that out there as an example. And as a final example, let me mention string topology operations. So let M be a compact manifold. And suppose we contemplate the homology of the loop space of M, right, with coefficients in the complex numbers. So this has an algebra structure. Which was defined by, introduced by Chast and Sullivan. This algebra structure has something to do with the idea of if you have some cycle in the space of loops and some other cycle in the space of loops, then you could consider sort of all ways that you could concatenate those two loops. And you get some cycle, well, it's of some degree adjusted by the dimension of the manifold because you don't expect a generic choice of two loops to intersect. So in fact, there's a lot more structure. You have operations on the homology of this loop space coming from Riemann surfaces with boundary. So for example, this Chast-Sullivan product you can think of as some sort of operation that you get on the homology of the loop space of a manifold. And the way that you get it is by contemplating maps from this pair of pants into the manifold and playing some games. And you can play the same games with more general surfaces. And it almost makes this thing into a two-dimensional topological quantum field theory. Not quite, because remember, last time I told you two-dimensional topological quantum field theories are determined by commutative Frobenius algebras. That means a commutative algebra with some kind of non-degenerate trace. And there's no candidate for the trace here, because some surfaces are not allowed. This surface, for example, doesn't give you string topology operations, but most surfaces do. The condition that you need is that every non-empty component of the surface has an outgoing part to its boundary. So it rules out for this picture, for example, but it doesn't rule out a pair of pants, and it doesn't rule out most more complicated Riemann surfaces. So this is an example of what's sometimes called a non-compact field theory. All right, so why am I giving you all of these examples? So first I'm giving them to you because I want to emphasize that this notion of a topological quantum field theory is maybe one that was motivated by something from physics, but it's describing a mathematical structure which comes up in a variety of situations. So here are three very different looking situations, and in each one you sort of meet a structure which you can describe using the language of topological quantum field theories, and maybe that will motivate for you why you might want to study them. I also want to call your attention to a feature that all three of these examples have in common, which is that all three of these examples, the field theory that you're getting is homological in nature, or it comes from algebraic topology. So for example, here the value of our field theory on the circle is given by the Hochschild cohomology of something. Here the value of our field theory on the circle is given by the K theory of something. And here it's given by the homology of some space. So in the first and third example, we could describe this by saying the value of our field theory on the circle is given by the homology of some chain complex of vector spaces. And in the second case, well, there's a similar thing that you can say, but it needs some fancier language. So now I want to contemplate for a little while that situation. Suppose we had a topological quantum field theory whose values on d-1 manifolds are given by the homology of some chain complex. Well, saying that we have a topological quantum field theory means that the vector spaces that are associated to manifolds of dimension d-1 are equipped with some sort of structure. In dimension 2, it was a Frobenius algebra structure. Now, in this situation, it's natural to ask if you can see that structure not just at the level of the homology of the chain complexes, but at the level of the chain complexes themselves. So the answer to that question is usually yes, provided that you think carefully about what it should mean to have a topological quantum field theory valued not in vector spaces, but in chain complexes. So that's what I'd like to think about right now. So here's our question. What should it mean to have a chain complex valued topological quantum field theory? So let's start out naively. So let's say our topological quantum field theory, we're going to denote it by Z. So in particular, so if M, let's say this is going to be a d-dimensional T of T. So if M is a closed n-1 manifold, then Z of M should be equal to some chain complex of vector spaces. And now if I have a Cobordism B,
N is D.
sorry?
N.
D, yes, thank you. Now if B is a Cobordism between closed d-1 manifolds, then we would like to say that Z of B gives me some map, is a chain map from Z of M to z of n. So far I'm just sort of naively translating the definition of a vector space valued TQFT to the world of chain complexes. But now we hit something interesting. So if we were to do this naively, we would say that if we had two Cobordisms which were diffeomorphic, then z of b is the same, well, z of b is equal to z of b prime as chain maps. And this is not the sort of thing that you see in examples. What you tend to see in examples is a situation more like that in order to define this chain map z of b, you needed to fix some additional structure on b, like a Riemannian metric or something like that. And that the map that you get on the level of homology was independent of the choices that you made, but the actual map of chain complexes might have depended on them. So this is too strong. This is not what you actually expect in examples. But you expect a little bit more than knowing that they induce the same map on homology. You expect them to induce the same map on homology for a reason. For example, you expect that if b is diffeomorphic to b prime, then, well, let me say it this way, less naively. If b is diffeomorphic to b prime, then z of b and z of b prime are chain homotopic as map of chain complexes. And you can do better. What you expect is that via a chain homotopy, which depends on a choice of diffeomorphism. So what I'm leading towards is that if you think about this sort of thing carefully, you're encountering, again, higher category theory. But you're encountering higher category theory for a very different reason than we did on Tuesday. So on Tuesday, we were thinking about topological quantum field theories, and we wanted to extend them by having them be defined on a larger class of manifolds of smaller dimension. So we were sort of extending down, and we were encountering n categories because of those manifolds of lower dimension. Here we're encountering higher category theory because we want to think not just about manifolds up to diffeomorphism, but we want to think about those diffeomorphism groups carefully. So let's try and describe vaguely the kind of structure that you might try to axiomatize here. So what do we want? Well, we want some sort z to be some sort of a rule which takes closed n-1 manifolds to chain complexes Cobordisms between n-1 manifolds to chain maps diffeomorphisms between Cobordisms to chain homotopies. And now there's no reason to stop here. We can sort of continue. Given two diffeomorphisms, you can contemplate whether or not those are in some sense the same. And the right notion of sameness here is that they're isotopic as diffeomorphisms. So you might contemplate what happens if you have isotopic diffeomorphism. Say isotopies between diffeomorphisms. Well, those should give rise to some relationship between chain homotopies, which I'll just say they give rise to chain homotopies between chain homotopies. And so on and so forth. So this sort of structure that you might want to study is naturally described in the language of higher category theory, and naturally described in the language of higher category theory, where you're not talking about n categories for any particular n, but instead you're talking about what, in my terminology a little while ago, is an infinity 1 category. So i.e., what we want is z to be a functor between infinity 1 categories. Where the left-hand side is an infinity 1 category, which I'll denote by, I don't know, let's call it cob n tilde. So cob n, remember, was an ordinary category where the objects were n minus 1 manifolds. Sorry, I switched n and d again, but hopefully it's not confusing. Morphisms are given by Cobordisms, and now for the ordinary, without the tilde, the ordinary Cobordism category, I identified diffeomorphic Cobordisms. They were just the same one morphism. But now I'm not going to identify diffeomorphic Cobordisms, but instead I'm going to throw in some two morphisms between them, which are given by diffeomorphisms. You could contemplate three morphisms given by isotopies, and so on and so forth. So this is another reason why you might want to contemplate higher category theory if you want to study these.
Will this one have the local property? Triangulated?
No, so this is not extended, so that's a good question. So, so last time we encountered higher category theory because we wanted to do exactly that. We wanted a more, this time we're encountering higher category theory because we want more refined invariance instead of, we want to see not just what's associated to, say, an n-manifold, but how the diffeomorphism group of that n-manifold acts on what we associate to n-manifold. So those are two different things that we can contemplate independently, but we can also contemplate them simultaneously. I could have, instead of introducing an infinity 1 category here whose objects were n minus 1 manifolds, I could have contemplated an infinity n category whose objects were points. Morphisms are Cobordisms all the way through dimension n, and then after n I contemplate diffeomorphisms. So that's where we're going eventually, or soon. How much time do I have? Probably not much. So, so I was told that I could take a little more time than an hour, but I don't want to keep people hostage here. So here is what I propose. So, so here I've motivated why you might want to think about infinity 1 categories, and I've sort of vaguely sketched an infinity 1 category that you might want to contemplate. Now, I haven't told you what an infinity 1 category is, but I promised that I would do that. So what I would like to do is take the rest of this time and give you a more precise definition of what it means to be an infinity 1 category, and give you a description of this guy as an example, as fitting into that more precise framework. So I'm not going to use this more precise definition anywhere in the rest of my lectures. I'm just going to work with higher categories informally after this lecture is done. So if you don't want to see that definition, then well, let's take a 5-minute break or something like that, and people who don't want to see the details can feel free to filter out and come back next week with no loss of continuity, and those who want to see the definition, I can show it to you.
Maybe 2 minutes, because we will have to finish in about 15.
In 15, 20 minutes. Okay, 2-minute break.
2 minutes.
So I am not sure if I'm going to get through this, but we'll give it a try. All right, so our goal now is to give some sort of a definition for the notion of an infinity 1 category. As I mentioned, there are many definitions that you might take, but I want one that's going to, first of all, generalize to give you a definition of infinity n category for any n, and one in which you can sort of easily accommodate examples like the one that we're interested in these lectures. So I'm going to present the notion of what's called a complete Siegel space. This notion was introduced by Charles Resk. So motivation is this. Let's say C is an infinity 1 category. And we don't yet know what that means. We haven't given a definition. But we know vaguely what it means. But what we do have a definition of is infinity 0 category. An infinity 0 category, we said, is just a topological space. So what we would like to do is describe C and all of its relevant structures in a language that we already speak, namely the language of topological spaces. So how might you extract a topological space from C? So step 1, or how might you describe C in terms of topological spaces, is take C. The reason C is hard to understand is that it has non-invertible 1 morphisms. So throw those away. So throw out the non-invertible morphisms. And then you get an infinity 0 category, a higher category in which all the morphisms are invertible. And I said that an infinity 0 category is just a topological space. So let's call that topological space X0.
Does this have a whole bunch of junk stuck to it, as if you sort of killed off some, what you might have...
Oh no, I didn't kill off anything. I took stuff out. This is sitting inside of C.
Sean's asking if
No,
you can
because
think of it
topological
analogous
space-
to attaching cells to a CW complex.
Think.
That's what I was thinking. You were saying before you were going to kill the homotopy parts above 1 or something.
No, that's not what we're doing. We're just, when I say throw out, I don't mean kill. I mean remove. This is something smaller than C. Okay, so all right, so this topological space is something you can think of as an invariant of C. You think that this topological space, its points are like the objects of C. And it's what you might call a classifying space for objects of C. So if C was an infinity 0 category, we would be done. All we would have to remember was this topological space. But in general, C has some other additional structures because there are non-invertible 1 morphisms in C, and we want to remember them. So step 2, let's try to remember non-invertible 1 morphisms. Well, what is a non-invertible 1 morphism? A non-invertible 1 morphism is a functor from, well, let me introduce some notation. If I write n with brackets around it, that means the linearly ordered set of numbers 0 through n. And I'm going to regard that as just an ordinary category. So there's a Hom from 0 to 1, a Hom from 1 to 2, and so forth. So in particular, what does it mean to give a morphism in C? It means a functor from this 2-object category into C. These form a category. If I consider all such functors, they form themselves an infinity 1 category, which I'll denote by functors from 1 into C. Well, we haven't really made much progress here. I was trying to describe C, and I introduced something more complicated than C. But as in step 1, there's a procedure by which we can simplify it. So let X1 be the classifying space for objects of functors from 1 into C. In other words, the infinity 0 category that's obtained by throwing away all non-invertible natural transformations between such functors. Now X1 remembers the non-invertible morphisms in C. Those are just the points of X1. But what it doesn't remember is how to compose them. If we wanted to understand how to compose morphisms in C, what we might try to do is think about a universal example of 2 morphisms that we can compose. What is a composable pair of morphisms in C? Well, it's a diagram like this in C. In other words, a composable pair of morphisms in C is a you can just think of as a functor from the 3 object category into C. Three objects 0, 1, and 2. We have a morphism from 0 to 1, a morphism from 1 to 2, and their composite, which goes from 0 to 2. And again, we can contemplate the collection of all such functors. That forms an infinity 1 category, and this has a classifying space, which I get by taking this and throwing away the non-invertible natural transformations, which I'll denote by x2. So more generally, for all n, let xn be the infinity 0 category, or topological space, obtained from functors from n into C by discarding non-invertible morphisms. So the claim, which I'm going to justify, or maybe I should write the thesis. So thesis, this collection of spaces, xn, together with whatever structure it carries, which I'm going to make more precise in a moment, remembers everything about C. In other words, it's a complete invariant of the infinity 1 category that I started with. So let me try to explain why you should believe this and what the relevant structures on this collection, what relevant structures you see on this collection of topological spaces. So let's ask, what structures exist on these spaces xn greater than 0? Well, note every monotone map f of linearly ordered sets from M to N, we would expect to induce a composition functor, which I'll denote by f upper star, from functors from N into C to functors from M into C. And therefore, by discarding non-invertible morphisms, that should induce a map from xn into xm. So in other words, this collection of topological spaces, there should be maps between them which are indexed by order-preserving maps from M into N. So we can summarize this. This sort of structure has a name. We should say that this collection xn for n greater than 0 forms what's called a simplicial space. So a simplicial topological space, or simplicial space, is just a collection of topological spaces together with a collection of maps, satisfying all of the sort of natural transitivity conditions that you would expect in this discussion. Now, this simplicial space is not arbitrary. This simplicial space satisfies, or we would expect it to satisfy, a condition, which I'll call the Siegel condition, which is that there's a natural diagram that you can write down. Here, I want to take this linearly ordered set of 0 through n plus m and decompose it into two overlapping linearly ordered sets. The part that goes from 0 to n and the part that goes from n into n plus m. So we would expect that in order to give a functor from this entire category into C, it should suffice to give a functor from this first part of the linearly ordered set into C, a functor from the second part into C, such that they agree on this common element n. That's a way of saying that we can compose morphisms in our category C. So this can be translated into homotopy theory, or into the language of spaces, by requiring that this diagram should be what's called a homotopy pullback square. In other words, I don't want to require that it be a pullback square. That would be in some sense too strict. But what I want to require is that xn plus m is homotopy equivalent to the space of pairs, point of xn, point of xm, and a path joining their images in x0. That path you should think of as sort of an isomorphism between the corresponding objects in x0. So, definition, a Siegel space is a topological space satisfying this condition. Simplicial topological space. Yes, thank you. Now, if you have a Siegel space, you can already start thinking of it as something that's kind of like a category. So let x dot be a Siegel space. You can define its homotopy category, which is going to be an ordinary category, where, as follows, the objects are going to be points of x0. And the morphisms, well, let's say Homs in this homotopy category between 2 points, x and y, well, you can define this as the set of path components. I'll write something and then I'll explain it. So what I want to say is that to give a Hom from x to y, what I need to do is give a point in the space x1. But it shouldn't be any point. It should be a point that projects to the points x and y that I started with in x0. But in this setting, you don't want to demand that it projects to it on the nose. You only want to demand that there's a path that joins the image of our point of x1 with x and the image of our point in x1 with y under these two projections. So that's what this means. This is an iterated homotopy fiber product, which means that I consider points in x1 paths in x0 that do the relevant things, and then I take the set of path components, and that's what I mean by Homs from x to y. And now let me just note, because I don't have very much time, that you can use the Siegel condition to define a composition. Well, a particular example if we take any point phi in x1, it defines a morphism in this homotopy category that I defined. Let me homotopy category, let me denote by h of x dot. And we'll say it defines a morphism from between its two images in x naught. Namely, I just think of it as a morphism by taking the two relevant paths to be constant paths. And now we'll say phi is invertible if this morphism in the homotopy category is invertible. Now, in general, a Siegel space might not have arise from the construction that I described a moment ago. It might not come from an infinity 1 category. There's an obstruction, which is you're supposed to think of x naught as a classifying space for objects in your infinity 1 category. In particular, you're supposed to think that all of the invertible morphisms in your infinity 1 category already came from x naught. In general Siegel space, that condition might not be satisfied. But you introduce one further condition. If x dot is a Siegel space, let x1 tilde be the subspace of x1, consisting of invertible elements. Definition: x dot is complete. Well, there's a natural diagonal map from x naught to x1. That's part of the structure that you have when you have a simplicial space. And that diagonal map automatically lands in the invertible elements. Definition: x is complete if this map is a weak homotopy equivalence. And you should think of this as encoding the idea that sort of any isomorphism that you have in the category that's described by this x dot is an isomorphism that sort of already exists in x naught. And now, let me just conclude by making an assertion. Which is that this notion of complete Siegel space is equivalent to the notion of infinity 1 category. So, depending on your point of view, this is either a thesis or a definition. You could say an infinity 1 category is a complete Siegel space, or if you have some other definition in mind, then it should be a theorem. So I think that I have spoken for too long already, so I will stop there, and we can.
Yeah,